Good morning. So thank you for coming that early to this talk. Well, I'm from University of Geneva. My name is Hugo Zbinden. I will talk about quantum communication, but essentially I will actually talk about QKD, which means quantum key distribution. And I will make some excursions to things related to that, but this is the main topic. I understood yesterday when I looked at the poster that you are from many different fields, actually. So, and also some people who are already, I think, know about QKD. But I will give this talk for absolute beginners. So I apologize for those who will be bored a bit. And well, normally in this kind of lessons, I would prefer that you ask questions all the time. So for technical reasons, this is not possible here, but I will make a break after the first part, and you can ask questions. And don't hesitate to ask questions, because I don't have to go to the very end of my talk. So I prefer that you understand little things, but you understand it, and instead of having many things. OK, so let's start. Well, maybe you know this person. No? This is Edward Snowden. And of course, all this affair around him showed us that nowadays secret communication is not only for banks and spies and everybody. It's really for everybody. Our emails are scanned. We are controlled. Big Brother is everywhere. You see there's a camera in front of me. I'm filmed. And if I make a bad joke, everybody will know tomorrow in the internet. No? So I think that's something we have to be aware of, that today we should be careful with our data. So very generally, what is cryptography? Well, that's, of course, I think you know, everybody knows, but I just introduce the key players in this game. No? It's this Alice who wants to communicate with Bob, and the bad guy is called Eve. And of course, they want to send some secret message. When I know nowadays people put this kind of stuff on Facebook. It's no longer like the early times, no? But still, let's suppose they want to send some secret message. And so they would encrypt this message with a key, which gives something which is completely unreadable for everybody. And then Bob will use a key, and he can decrypt and see the message. No? OK. Now, classically, there are different ways to do this, no? And so this is about maths. It's no longer physics. No, it's actually, and I'm not a specialist in this, but anyway. So we have different schemes which are based on complexity. This means that you don't have a proof, a mathematical proof. It shows that it's impossible to decrypt. But it's fairly hard, no? And then we have these schemes like DES, those data encryption system, and AES, advanced encryption system. So these are standards where you have a secret key. Like I showed before, Alice and Bob have a rather short key, and they use this, no? And then there's another scheme, which is this public key scheme, which is very useful if you want to order something at Amazon. No, I never met Mr. Amazon before, no, so I don't share a secret key with him. But nevertheless, he has this public key system. So there is a public key, the key of Amazon. Whenever you log in actually you go to a server, to a trusted server, and then you get this public key. You will use this public key to encrypt your data, and Amazon, we are the only ones who have the corresponding private key to decrypt it. Actually, it's a rather detailed. Actually, this is very time-consuming, this way to do. So actually, in practice, what you do, you don't use this public key scheme for the whole communication, but we just establish a session key, which is a key like this. And then once you have this key, then you OK. Now, well, these public keys, the idea is that you have a one-way function. That's something that you can compute easily in one direction. But the other way around, it's hard, no? Like this. So it's easy to encrypt with a public key your data, but to decrypt this seems to be impossible. And of course, this one-way functions is something that mathematicians think it believes, but it exists, but in practice, it's really, as I said, there's no proof that there are really good one-way functions. And this scheme here is based on this problem of factorization, no? So you see, this is, if I give you this number, 5,671, no? It may take some time for you to find out what the factors are, no? But of course, this here, 107 times 53, it's easy to calculate. So this is an example of this one-way function. No? And well, now we have this quantum physics, quantum information coming, and people come up now with this quantum computer. And this person here, this is Peter Shor, who actually found an algorithm where this kind of calculations, you could do it much faster with a quantum computer than with a classical computer. So this, if you have a quantum computer, see, this is a picture of D-Wave, this somebody who advertises that they have a quantum computer. Well, we know that this quantum computer cannot yet solve this kind of problems, but still, if you have a quantum computer, all of a sudden, these public keys will no longer be secure. Okay, so there is another way to encrypt, and it's a very old thing, actually. And it's called this one-time pad. And the idea is here that you have your text, no, in a digital way, and you just XOR or add a key which is as long as your text and which is completely random. So if you do this, of course, your ciphertext, your encrypted message, will also be completely random. And something which is completely random, there is no way to get any information out of it. So it's a rather simple proof we can do that you can show this is perfectly secure. Well, the conditions are, of course, that this is really random and not pseudo-random. Huh? And you can use it only once. If you use it twice, then it's no longer secure. So now a problem we have a secure system, but we have long keys and we have to distribute the keys. No? And this is now where quantum key distribution can play a role. No, that's the point. Okay, so as you understood now, quantum key distribution is not a new cryptology method or something. No, it's just a way to distribute the key. And the idea that quantum physics guarantees this secure transmission. So the idea is actually that in the films, you see sometimes a guy like this with his suitcase and he brings a key from A to B, no? And the idea is, of course, that in this case, no, you will ask the guy when he arrives at destination, everything was okay, no problem, blah, blah, and he said, yeah, okay. So if you trust the guy, then it's a good way to do it, no? And of course, you send the key, not the message, no? It's also important. If a guy gets killed and it's lost, so you send first a message and then a key and then a message, sorry. Okay, now what we want to do, we want to replace this guy by a machine which sends now this keys via optical fiber, and then we can prove that QKD is actually information theoretically secure. Okay, now there are different ways to implement this, no? And I will present you a very standard scheme which was invented by Bennett and Brasser in 1984. And well, it's based on single photons. You will see later on that actually in practice we don't use single photons because single photons are not so easy to produce, really single photons. Huh? But still, let's suppose for a time being that we have single photons. And now these single photons, you can use different degrees of freedom, and I think the simplest way is to use polarization. So we say, okay, we have these photons and we can polarize them in some direction. No? And of course, we have, well, Alice has his light source, or light source, and you have these polarizers. And then you can encode, let's say, a horizontal photon is 0, a vertical photon is 1. And then you have another basis. You can use 45 and minus 45. And you can send photons like this. And of course, Bob, if he uses an analyzer, a polarization beam splitter, who can distinguish between horizontal, vertical, or 45, minus 45, he can measure, detect the photon and know which bit value Alice sent. No? Of course, if you do this just to transmit data, you use only one basis. You don't need the second one, no? We need the second one for security. And it's an important thing. That's what you say here, no? Because, Alice will choose randomly between these 4, and Bob has no idea actually which state he sent. So what he can do, he can also just choose randomly one of the bases, no? And from time to time, he will choose the right basis, and he will get a right result. If he chooses the wrong basis, then it's a random result, no? You know that if you have a vertical polarized photon, which comes to 45, minus 45 polarization beams, it will be random. And you see, it's a bit how it works. Now here, you see the series of photons. Let's look at the first one. So Alice sent this photon here. And now let's say, in this case, Bob used this basis. And of course, he can get some result, random, which is in this case wrong, no? It's a 0. But whenever they use the same basis, like here, he will get the right result. So half of the time, this scheme will not work, no? And so Alice and Bob have to communicate later on and say, okay, when does it work and when not? And they have to throw away half of the data. So we only use the keys, which corresponds, you see here, this is roughly half of that, no? Okay. Now, if an eavesdropper tries to attack, no, he's the same position like Bob. And you can see the idea. Let's say Alice sent a vertical photon, and now an eavesdropper, like Bob, he can choose randomly one of the 2 bases, no? Well, let's say he uses the right basis. And if he makes an attack like, that's what you call intercept resent, so he tries to measure a photon, gets a measurement result, produces a new one, and sends it to Bob, no? This is this kind of attack we're considering here. So you see, of course, since he used the right basis, he will get the correct answer. He will send this photon to Bob. And now we are considering only cases where Bob uses the same basis like Alice, no? Because we know if Bob uses another basis, they will throw it away anyway at the end, no? So now Bob chooses also this basis, and of course he will get the right result. And he will be happy, no? It will be okay. But now, if Eve uses the wrong basis, no, which happens in 50% of the chance, she will generate either a photon like this or a photon like this. And now, when these photons are measured by Bob in this horizontal vertical basis, again, by 50% chance, Bob will detect a vertical or a horizontal photon, no? And now you see, with this kind of attack, in 50% of the cases, this action of Eve will introduce errors with 50% of chance. So in total, we'll introduce an error with a probability of 25%. So what Alice and Bob now have to do, so they have to communicate again. They exchange a few bits and randomly, and they compare them, and then they check if there are errors or not, no? And if there are no errors, then they're happy. If there are errors, they know something went wrong, there's an eavesdropper there, no? That is the idea. And you see, actually, well, this is when they do the attack all the time, but of course, Eve can choose to make the attack from time to time. And the information of Eve, this is the way you write it, information between Alice and Eve, is just twice this error rate Eve introduces. Okay, now in practice, of course, you always have errors, no? Experimental limitations. So you have to be a bit more, make a more careful analysis of this. And actually, if you have errors, no, Alice and Bob exchange bits, and they have errors, then you can correct errors. No, that's standard in telecom. Normally in telecom, the errors are the order of 10 to minus 9 or 11. So it's easy to correct errors. Now in this QKD, unfortunately, the errors are quite often higher, a few percent. But still, even if you have errors, you see how the information from between Alice and Bob decreases as a function of the errors. No? So of course, if you can imagine if you have 50% of error, then there's no information at all anymore. No? And okay, so the information and Alice and Bob goes down if we have error in their communication line. This is this way of Shannon to calculate this. This is this Shannon entropy. You can calculate this is the probabilities to get a 0 or 1. And it goes down like this. Now we have seen that if this attack I just presented to you, Eve gains information the more error she introduces. No? And her information increases like this, as I said, with twice the quantum bit error rate. So she can go up to 25% of errors, and she would get, in this case, 50% of information, because in 50% of the cases, she was right, no, with her base. Okay, but you still see there is a difference between these two curves, and this difference can be used to create a secret key. And actually, this attack, I showed you this intercept resend attack. It's not the best attack Alice can do. She can do more powerful attacks. I don't go into detail how, but you see, still, even if this ideal attack, you have some secret key rate you can distill. Okay, so I try to summarize now a bit our scheme, no? So I remind you that Alice now sends lots of photons, no? And then we have losses in the channel. We have bad detectors, and eventually Bob detects a few, no? So, of course, the number of detections is much smaller than the number of percent. And then you start this discussion over a public channel where you make this what we call, well, first of all, Bob tells which bits he got. So Alice now has the same amount of bits. And then you make this discussion about the basis. And in this case, what is half of them can be used. No, this is the safety key. Then you use some bits out of the safety key to estimate the error. And then you have to correct the errors. And then you make this privacy amplification. So this privacy amplification is that what I showed you before. No, it's this procedure you have to do to get this secret key rate here. And this is actually, in principle, quite easy. No, you have to. The idea is that you make a calculation where Alice and Bob, who has a whole information, can do, but Eve, who has only a little bit of information, cannot do, and at the end, she has no information at all. And I can maybe give you a very simple example. No? Let's say, for instance, Alice and Bob exchange 2 bits, one a 0 and a 1, and Eve knows one of them. Now, we don't know which one, but it doesn't matter, no? But now what Alice and Bob could do, let's make a calculation. We take just the XOR of these 2 bits, no? So this will be 1, no? But now the eavesdropper, who has only 1 bit, has no way to find out what this could be, no? That's an example how you can make this privacy amplification. Of course, it's a very bad technique because you lose half of the bits, no? But in practice, you can do that much in a better way that you don't lose too many bits. And then a final step, which is very important, is this authentication. No? Once you have finished all these communication steps, you have to authenticate it. No? You have to be sure that you really, Alice has to be sure that you really talk to Bob. Of course, she talked to somebody else, it doesn't work. No? And then this is a way to prevent what we call a man-in-the-middle attack. No? The eavesdropper could stand in the middle between Alice and Bob, look at Alice and pretending he is Bob, and then make the whole game, and then make the same thing again with Bob, no? And for this, you need this authentication. And of course, this authentication means you have to share some initial secret, no? And so you have to know a person, of course, no? That's the point. And in this QKD, so at the very beginning, you have this initial secret you share, and then you create a new key, and part of this new key you will put aside for a next round as an authentication key. No? So then it goes on forever and ever. But in the very beginning, of course, you have to share a secret. Okay. Well, maybe that's just the first experiment which was shown in 1989. It's a very short distance. We have some box cells here and so on. And this is it's a more recent scheme. That's something it's a result of a Swiss project. Well, you don't see that much, but you have these racks. But actually, there are 2 boxes in these racks, essentially. Well, there are 3. There's a computer, a box which exchanges the keys, and then there's another box who encrypts the data. No? Okay. Well, and then maybe I make a stop here. So maybe I should make a short stop for questions. Do you have questions? Now where are we? Well, this is what I wanted to show. This is this very first experiment, and now this is a more recent one, and this is kind of a state of the art. So this is to show we can go over to 300 kilometers. And now, of course, in this state of the art thing, it's no longer like the example I showed you. No? So actually, I will not go too much in details, but actually we don't use polarization, first of all, to encrypt or to encode the bits. But we use a scheme like this, where you actually send a series of pulses. And then a way we encode a bit is we have 2 time slots, no? And if a photon is, let's say, in the first one, then it's a bit 0. If it's in the second one, it's a bit 1. And from time to time, we send 2 pulses. And then we send it through down the line. So we have a CW laser, we have an intensity modulator. So that's now we have an interaction with people here who make intensity modulators. And then we attenuate to a low level, and then we send it down to a line. And Bob, it just detects here when the photon arrives, and he gets a bit value. Of course, this is not secure. Now we have to introduce some way to check if somebody attacks. And that's why you use part of a light. You don't send it to this detector where you measure the arrival time, but you send it to an interferometer. And this interferometer here, you measure now the coherence between 2 succeeding pulses. And now if an eavesdropper tries to measure when the pulse arrives, he will destroy this coherence. And so you measure the visibility of this interference fringe here. So actually what you do, you adjust the phase here. Maybe I should say, no, the difference of this is an interferometer which has a short arm and a long arm, and the difference of arm length corresponds to a difference in time between these 2 pulses. So if a first pulse takes the long arm and the second pulse takes the short arm, you can have interference. And you adjust the phase in a way that you never get a click here. And now if somebody actions on your line, he will destroy this coherence, and you start having clicks. So the idea is actually that you measure this visibility here. You can measure also the error rate, of course, you get in your data here. And this is now the input used for this key distribution. And this you can do very quickly. We have the 1.25 gigahertz clock rate. So it's easy. It's easy. You don't have to change polarization, and you have here in optical fiber polarization is not maintained. You have to stabilize it and so on. So it's a better way to do. And so you see the results, what you get here. No? You see, as a function of distance, how our secret key rate goes down on this, following this red curve. So if you go to 300 kilometers, you end up with 10 bits, something like this. And what's very important, of course, is that you have low noise detectors. That's actually just a bit the most important thing. If you go to far away, since your signal goes down and down and down, but the noise of your detectors, of course, stays on the same level. And at some point, the signal-to-noise ratio is very bad. And this means that you have a lot of errors which are created by the noise of detectors. And that's why you see well, I don't go into details, but you can, by changing the temperature of the detectors, you can actually optimize your scheme. And if you go very far, you need very, very low noise, so you go to lower the temperatures. Okay, that's a more technical thing. Of course, you also use good fibers. And the best fibers you get now is on this order of magnitude of 0.16 dB per kilometer. Okay, now a question you could have is, well, this is just a picture of how it looks like, this prototype. And here's more a technical layout, but I think I skipped this. Okay, now, a question we can have, can we go further, no? And the first, maybe a stupid thing you could think, so you say, okay, let's amplify the signal, no, like in telecommunication. And actually, that's a question sometimes arises. People say, oh, well, now we can amplify, whatever. And of course, the question will be, or the answer will be, we cannot amplify, no? But let's still consider this, no? So what happens if we amplify a signal? Well, we could, for instance, try to use a erbium-doped amplifier. I don't know if you know this. This is it's a three-level system. You excite your system, and you can have spontaneous and stimulated emission. So if you come in with your photon here, you have your fiber here, you generate more. Let's say it's a horizontal photon here, or this red one. You generate more of this red one film, and then you can amplify your signal. Of course, the eavesdropper could also try to do this, no? And this, of course, would be very bad. No, he could amplify the signal, take a few photons on, and send the other photons to pop. But now, I said you have not only stimulated emission, but also spontaneous emission. And if the spontaneous emitters are these blue photons, so if you measure now the polarization, you will get indeed a few photons which have a right polarization, but also photons which have a wrong polarization. Because the spontaneous emission, of course, has no preferred polarization. No? And now you can measure the fidelity of this amplification process, and it's just the ratio of a power you measure in this detector divided by the sum of the powers. And of course, if this signal is very small, this fidelity is very bad. If a signal is very strong, like in telecom, no? Yeah, they still have strong signal, then this ratio is very good, and the noise is not so big problem. And you can actually calculate this fidelity, no, as a function of the average number of photons you have in your pulse. And you see if you have only one photon, no, which is the case in QKD or even less, then you see this fidelity is rather bad, 66.6%. This means in 1/3 of the time you make errors. And this is exactly these errors which Alice and Bob would realize, no? What is quite nice with this, no? You see this fidelity, and it depends on the number of photons. So what you can do, actually, you can use this kind of experiment, no? You send in some light pulse, which you don't know the intensity, but you know the polarization. You polarize it in a certain way, and then you measure this ratio here, which is a relative measurement, and you can determine the number of photons in the pulse. So actually you have a radiometer. It's an absolute radiometer. You don't need some reference in Paris or whatever. Just in your lab, you can generate a radiometer by doing this, no? And that's something you can, if you're interested in this, you can read this in this paper here. Okay, so now this erbium-doped amplifier does not work, no? Apparently. Now, actually, maybe you're not convinced, but it's the right approach, but they actually can quite easily prove that you cannot clone a single photon, you cannot amplify it. And this is the proof which appeared in, actually not that long ago, it's 82. And it's a quite simple idea, and the idea is like this, no? So, well, this is how to copy a quantum state. Of course, we cannot just measure and prepare. That's what is our receive and send attack we discussed. But you could say, okay, I take a universal cloning machine. And a universal cloning machine would be something like if you have a state alpha, you will produce twice 2 photons with this. Or you have a beta, you will produce 2 photons beta. But now you can easily prove that you cannot work for any state, no? If you have this machine which works for these 2 states, you would also like to make it work for a superposition of these 2 states. So if you have A times alpha plus beta and beta, actually if you apply these rules now, you realize you will get this, no? And it's not what you would like to get, because you would like to get this twice, no? You would like to get this once and twice, and it's not the same thing. So it's very easy to show that it's not possible. And actually, this erbium-doped amplifier I showed you before is actually an optimal cloning machine. You cannot do better than you can do with this erbium amplifier. Okay, well, maybe another thing you could ask if you're still not convinced, no? You could say, oh, what would be possible if cloning worked? So it's actually some fundamental thing, this cloning, no? It's a bit strange, no? And actually, I can show you, if cloning worked, you could make superluminal communication. And this, I hope you believe that it's not possible, no? Okay. Well, let's look at how like this works. So, well, now it's a question I have to you is, have you seen already this entangled photons and Bell experiments and something during this week? Okay. Well, anyway, so that's, I try to explain that, no? Very quickly. Now you have a source here, and this is a source. This is a parametric down conversion source. Now you know everybody with these nice nonlinear crystals. And you generate photon pairs. And these photon pairs can be in an entangled state. And an entangled state means that if you write the state of these two photons, 1 and 2, you cannot, this function is not a product state with describing one photon and the other photon. The properties of one photon is linked to the other. No? So we have, for instance, this state here, which we have polarization entanglement. Then you showed, you know, if a first photon is horizontal polarized, the other one will be vertical polarized, or if it's vertical polarized, the other one will be horizontal polarized. But the state depends on, well, the second one depends on the first one. This means that actually the photons, before you make a measurement, they are unpolarized. You have no idea about the polarization. But once you measure one, in any direction, not only in horizontal, vertical, in any direction, you know that the other one will be orthogonal. And you can use, so you can do now, you can play this game. Now you have analyzers where you change the angle, and you have two detectors. And if these angles are at 90 degrees, no, then you will get perfect correlation. And if you are at some angles, you get different correlation. So actually what you can do, you can make a Bell inequality. And this Bell inequality is something which describes these correlations. And you can prove that, well, now I'm a bit quick, no, but you can prove that there are no hidden variables who explain these correlations. No? Because the funny thing is really that it's a bit strange, no, that you have two photons which are far away, and you get, whenever it's completely random, no, this photon can go this to this detector and to this detector, but if the settings are right, by some magic, if this goes to this one, the other one will go to this one. No? It's always the same. It's random, but they are correlated. And one way to explain this is this hidden variables models. So they say, that's what Einstein and Podolsky-Rosen came up. They say, well, there's a problem with quantum mechanics. Now, if you have this, how can it be that two separated schemes have this correlation? And they said, our knowledge about the scheme must not be perfect. So there must be some hidden variable, and which explains everything. So actually, the photons are pre-programmed to go to this detector, and the other, of course, has the same program. And now with this, that was the achievement of Bell, with this Bell inequality, you measure these correlations, no? And the way you measure it, you know, we have these two settings, use two settings on both sides, and you have then 4 different combinations, no? And you calculate the probabilities for this different probability to get these coincidences here. And actually, I just see an error here. All is alpha, beta, all the same. But we have alpha, alpha prime, and beta, beta prime. You have 2 settings, 4 combinations. And then you get here, you have this expectation value, calculate these probabilities, you make this inequality here. And if this value S you get is bigger than 2, you can prove there are no hidden variables. This has been done many times by Alan Aspect and so on. Okay. That's easy. Let's use this system here. Now, let's come back. How could you use superluminal communication? No? The important thing is, this is random, I told you. No? Even if you have these correlations, since the results are random, you cannot use that for superluminal communication. No? That's the point. It's not a contradiction to relativity. But now, imagine if you could really clone a photon, no? That's that point, no? So if I could clone a photon, I could use a scheme like this, no? I could say, okay, Alice measures in one basis, either in horizontal vertical or 45 minus 45 degrees. And now, you know, if Alice and Bob use the same basis, the results are perfectly correlated. If they are not the same basis, they are not correlated, no? So if Bob uses the same basis, he will get always the same result. Now, if Bob makes many, many clones of his photon, he will measure many, many times. And if he always gets the same result, he knows I use the same basic like Alice, no? And if he does not get the same result over time, he knows he has the other basis. So in this way, they could communicate. No, Bob could find out if Alice used this basis or this basis. So the quantum cloning is linked to superluminal communication. No, it's really a fundamental principle, that you cannot clone perfectly. Okay. Well, now it's a bit strange. No? I told you all the things you cannot do. You cannot measure a system directly, perfectly. You cannot clone it, and so on. And now maybe you have heard about teleportation, no? And, well, you certainly heard about this part of teleportation. And then, well, when was it? In 93, people made a paper and said, we can do quantum teleportation. And there was a big excitement everywhere, and we could ask yourself, why? You know, why is it special, no? And actually, teleportation is a very stupid thing, no? In some sense. It's of course, instead of traveling and moving an object from A to B, you just send a plan of the object to A to B. No, if I want to teleport this desk, no, I will just say, okay, it's big like this, made of this wood, send the plan to the other guy, and he will reconstruct the same desk. Now, which is for a classical object is obvious, but for a quantum object, since I cannot measure it, and I cannot clone it, no, if I reconstruct it on the other side, of course, kind of make a clone of it, it seems impossible. And that's why it was a surprise that it actually works. And the idea, why does it work? Well, the idea is that you use this pair of photon pair sources I just told you, no? And then the idea is you have your unknown state. You need one of these photons. You make a Bell state measurement. I will tell you a bit more about what this is. And then, since these two photons are linked, no, some way, you manage to kind of transmit the information about this object to this one. But you need to send some information. That's important, no? So just to summarize, now what does it mean? What's important, you destroy the original here, so you don't get a clone. You still don't know the object, what it is actually. There must be some classical communication, otherwise it will superluminate. And that's the thing, no? And now how we do this, a bit more in detail. You know, you use this quantum state here. That's this entangled state I showed you before. It's just another one. It's not the psi one, but a phi plus state. And you have your quantum state here. It's a qubit, no, with a superposition of two states here. So you don't know this qubit, and you would like to teleport here. And you have this state here. Now we make a measurement here. And this Bell measurement actually describes this common state. Now this photon here and this photon here, or this particle. And it can be in 4 different states, these 4 Bell states. And now if you assume you get this result here, no, for this photon here, then you can calculate or easily find out that the other one is now in this state here. So now for this case, you see actually, this is actually the initial state. So this photon here will be in this state here. So we teleported it, no? But now you see if you get other result here, it's slightly changed. It's still almost the same, but the sign changes. You have to flip a bit or and so on. So what is important that whenever you measure this, you get an outcome. You have 4 possibilities, one of these 4 blue states. You get 2 bits. You send it to the other side, and you apply a transformation on this qubit. And then if you apply this transformation, you get always the initial state. We still don't know which one it is, but you can teleport it. Okay. And how do you do this? Well, in classical physics, linear optics, linear optics, actually you can only measure 2 out of these 4 Bell states. And the basic idea is to use this Hong-Ou-Mandel interference. I don't know if you had heard about this, but you know if you have 2 photons coming, which are not distinguished from here and here, we will bunch, no? So this means that we never go 1 here and 1 here, we go always 2 here and 2 here. And then this is this probability to detect a coincidence as a function of time of arrival. So if they really arrive at the same time, it goes to 0. That's just this Hong-Ou-Mandel dip. And this, you use this kind of measurement in order to make this Bell state measurement. But then you cannot distinguish all the 4 states. It depends a bit how, if you encode in polarization and so on. So it's, with an explanation I can give you, cannot understand everything. But okay. Well, then you can make this teleportation. That's something we did. And it, see, oh, we don't see anything. It's just sort of set up. But the important thing, it works, no? But a very important thing also, it works almost never, no? And it's also, for one state, a degree of freedom of a photon, no? Polarization, whatever. So you can really be sure that it will never be possible to teleport a macroscopic object, no? Already the data you should have to transfer, this will explode. Okay, so now, well, I have still a lot of things, but I think we have to stop here and make another session of these questions. Thank you for your attention. Now, we understood teleportation, where I can teleport a single photon. And I also can teleport entanglement in some way, no? And the idea is this. This was the teleportation scheme, no? But now if you can start with an entangled photon pair here, you can make a Bell state measurement here, and then you get this photon and this photon are entangled at the end. And I use this now in order to explain you the quantum repeater, no? Because yeah, we had some interruptions, but the question was, can we go further than these 300 kilometers? No? And we already realized with all this cloning stuff that we cannot amplify the signal. Now there is another solution, and this could be this quantum repeater. And for this quantum repeater, we need this process of entanglement swapping. So this is this teleportation of an entangled state. Okay, how does this work? Well, you know, if you want to, well, these are quantum memories, no? These yellow boxes. So I don't explain you how this really works, but this is actually in our lab we use this rare earth-doped crystals, and we can absorb a photon in an ensemble of many of these ions, and then we can absorb it, put it some state, and can re-emit it. It's a black box for you, no, for the time being. So it's just a device we can store a photon and release it at some point without knowing the state of a photon. No? Okay, so now if you have a link, no, a very long link from A to Z, and if you would like to send a photon just through the link, and you have these individual links here, no? There are many intermediate stations, but the direct transmission would go to 1 over eta t. So eta t is the transmission for one link times to the power of n, no? If you have n links. So if you have a chance that the photon from here to here goes with 10%, then it's 10%, 1%, 1 per mil, 10 to minus 4, and so on. No? It goes down very quickly. So now the idea is to make it stepwise. So you said first, you establish entanglement between these 2 points, establish entanglement between 2 points, between these 2, and so on. So we have each time 10% of chance that it works. But then once it works for all of them, you start your procedure, which is this quantum repeater procedure. So once you have in all these quantum memories, a photon which is entangled with the other one. You make an entanglement swapping, that was this procedure. Make this Bell state measurement here, and then you get this one with this one entangled. You make it here, you get this one with this one entangled. Then you make a measurement here, you get this one with this one entangled, and so on. So that's the idea. You kind of, since the chance that if you send a photon directly through a very long fiber is very, very low, so you kind of send it over shorter pieces and verify that it happened for all the pieces. And if you do this, this time it takes to transmit one bit now just goes with 1 over eta t. Because essentially you can do that in parallel. You try in parallel all these links, and if it works with this probability. Okay. Now, so that looks very good, and people are talking about this quantum computers for a long time, but of course in practice it's not so easy. But still, if you now you can try to think out how we would do it in practice, no? And well, this is what I showed you before, no? It's with these two entangled photon sources, no? You get this Bell state measure and you do it. And actually, one of my colleagues, is Nicolas Sangoire, he found out that you can do it more efficient way if you use single photon entanglement. And what is single photon entanglement? Actually, you don't have a photon pair source, but you have just a photon source. You send it on a beam splitter, and now the photon can be either here or either here. And you have a kind of path entanglement. Now you have a superposition of a photon being here or here. No? And if you do this, so you can imagine now this Bell state measurement is really very simple. No? Just one of these detectors will click. If you get a click here, you don't know if a photon came from this source or from this source. No? But so this means actually, let's say if if a photon is not going in the middle here, no, he goes to this quantum memory. But if you detect one photon here in the middle, not knowing from where it comes, it means the same thing like now in this memory or in this memory you have a photon, but not in both. So now we have this entanglement, this single photon entanglement transported to the memories. We swapped the single photon entanglement. Now this memory is now entangled with this one. We have excitation here or here. So it's a bit similar like this. Now it's just with single photons. No? But this Bell state measurement here is now very simple. Here it's a bit more complicated. No? Okay, but it's just, it's not really the message. No? The message is that you know how to construct this. You use photon pair sources, you use memories, you have all these detectors. On paper it's quite straight away. And you can calculate this. No? So you calculate now the probabilities and the times and so on, being very optimistic. No? For instance, in this case, for this calculation, which is in this paper, we assume, for instance, for a heralded single photon source, you have a P1 of 95%. So yesterday we had a poster where, I don't remember, it was, what was it, 80% or so? It was not something like that. No, it was less, 50%. Ah, okay, so this is really, well, we can, it's a, we are very, very optimistic, no, in all cases. So we have quantum memories with, I put only this probability, but essentially all probabilities are in this order. No detection probabilities, the probability that quantum memory works, and so on. And if you use this, 95% for all this, and the clock rate, of 10 gigahertz, then this is the times you get, the times it takes to transmit one single bit. No? So if it's just a direct link, no, over 1,000 kilometers. So 50 kilometers is 10 dB loss. No? So 1,000 kilometers is 200 dB loss, so 10 to minus 20. No? Now if you use 10 gigahertz, so 10 to 10 trials per second, with 10 to minus 20, you still end up with 10 to 10 seconds. It will take, in average, that a single photon goes through 1,000 kilometers. I don't remember how much years it is, but it's too long, no? Now, the quantum memories, all these quantum repeaters are very good, no? You see, indeed, that was the purpose of this paper, no, to show that the single photon entanglement is better than the other scheme with entangled photon pairs. But still, if you don't care too much about this, if It's much shorter than 10 to the 10, of course, no? But it's still long, very, very long, being very, very optimistic. So even if conceptually this quantum repeater is a very nice concept, and also quantum memories and so on, it's not a very good solution for QKD. And we are talking about QKD here, as I said to you in the beginning. It's all about QKD. So it's not a very good solution. So what people do now, they put what they call trusted repeaters. It's for a physicist, it's not very interesting. No? We just have many links, and also, and in between this, you just put it in a safe, and then you trust that nobody can hit it. So there are many, many things going on in China. They make a link between Shanghai and Peking over 2,000 kilometers with each link, I don't know, 100 kilometers. So it's really a huge project. And this is another project, it's happening in the States now, from Columbus. It's here. But here is Washington, more or less, Washington area. So they want to make a link between this, and it's 770 kilometers. I think we're a bit late. I don't know. Okay. Anyway, now this is, of course, if you are a government, no, that's maybe a solution you can check. It's okay, you have intermediate links, or if you have a bank with many offices and so on. But you can also make it a bit more complicated. Then you have a network, and if you want to distribute entanglement between here and here, or a key between here, you go here this way, you can make different ways that if a bad guys control one link, you can still make different keys with different paths and XOR the keys in order to get some more security and so on, but it's not very satisfactory, you know? And in particular, it's satisfactory for these guys, no? Because they just have to control a bit the network, and then everybody believes that everything is safe and secure, and for them it's actually a good way. They promote this pretty much, this network thing, no? Or a trusted repeater thing. Now there are other options to go further. Is this, well, that's what I said. You can go to space. Now there are a few projects like this also in China. It's easy to get money. Well, you need a lot of money, that's a back, but it's quite sexy, no? And there are also people doing with planes or with drones, no? That's quite smart, no? You have a drone, it goes on one office, you exchange the key, and then the drone flies to the other part. Or a drone can be very high, and it exchanges key directly, and so. But still, you have to trust the drone, no? Okay. It's not very. Okay. So now, okay, let's close this part of this distance. So it's not so good use, no? It's not so easy to go far with QKD. And now, maybe I would like to, the last 10 minutes, I would like to mention another aspect about this practical security of QKD. Because now I always said everything is perfectly secure and so on, and maybe you have read in the newspaper, there are some hackers, and even QKD is not secure and so on. And I just took one of these headlines on some blog. And indeed, where it happened that people hacked QKD systems. So I think it's important to remind that this can also happen to any crypto system, and this is another example I found on the internet where I use this. This is the best RSA thing you can imagine. This is this private key thing with keys of 40,000, and the guys just managed to crack it. They put a microphone beside the computer, and they look at the sounds. And they managed to make some correlation. I don't know why. It seems to be completely impossible, no? But they managed to crack this system, no? So this is not because this algorithm RSA is completely insecure, but indeed there are some problems in the implementation of this, no? So it's important to remind that if you have these pillars which guarantee you security, you have this, for public key, you have this assumption of a difficulty, mathematical difficulty, of course. But then, of course, what is this? When you were study of this classical computer model. And in quantum key distribution, you have this column of the quantum physics must be wrong. These are the basics, no? But then, of course, you have to add columns which say you have to implement it in a correct way. That's too normal, no? We cannot guarantee, even if in theory, if you made an error in implementation, then of course it's not working. Okay, so it's important to know that QKD can be broken, but a specific cannot be broken, but a specific implementation can, possibly. Now, it sounds like hopeless, no? Now we have a perfect scheme, but still it can be broken and so on. And at the end, we have to trust that it's okay. And now, well, quantum physics come up with a new solution. We can make device-independent QKD. Sounds great, no? So we can actually guarantee the security completely independent of a device. Even if a guy made it completely bad and a lot of errors with backdoors and so on, you can make a test, and if the test passes, you can be sure that it's secure. And the idea, well, the idea is nice, no? The idea is that it's based on this entangled photon pairs which I introduced to you. So remember, no, we have these sources, we send particles to Alice and Bob, we have this measurement apparatus, they choose a basis, or measurement setting, X and Y, we get some result A and B. Now, if everything is okay, we have really this entanglement, then you have these strong correlations between A and B. Now we can check this, and you remember also these outcomes are random, no? They are correlated. That's what you need for a key, no? They need to be random and they must be the same. Now, which is good, that this Bell inequality, is very, very general. So if you can violate the Bell inequality with your data, you know there is no hidden variable. So it's nothing hidden inside. So it's completely random and so on. And this, you can translate it now in this picture with the eavesdropper. If there was an eavesdropper, the eavesdropper has some information about the state, which you don't. And if you violate the Bell inequality, you can prove that it's impossible to have some information. So it's really, if you can violate the Bell inequality, you can be sure that these two outcomes are random. And the only condition is that the inputs you give here, you choose this in a random way, of course, and you have some free will, that you decide which input you give. But of course, if the input is known to the eavesdroppers, then it's bad, But if you have, with this condition that you have this input, you can give an input, then you can use a completely back blocks here, and you look at the output, and if this output has this correlation with Bob, you can be sure that it's secure. That's very nice, no? Well, the drawback is, in these Bell experiments, I didn't tell you, also in these Bell experiments, these photons are detected not all the time, quite rarely actually. And you make an assumption that the events you detect are a fair sample of all photons you send, which is pretty reasonable, because we don't think that physics want to fool us or whatever. We believe in laws and they're always the same, and even if I measure not all the time, it's okay. But here it's no longer the case. Now here you have really to guarantee that this efficiency is good enough. Because here a bad guy could really spit out only the results when he is happy with the settings, or something. So that's problem is now you have to make a required efficiency is 82.8%. So this means if you send out the photon here, in 82.8% you would like to have a result. And now the problem is, if you look at the transmission efficiency of 10 kilometers of telecom fibers, it's only 60%. So it's desperate again. Now it's okay, come on, I cannot. Even a little distance, I lose photons anyway, so it cannot work. Now it comes another, it's not yet lost, it comes another nice idea actually. And this is the qubit amplifier. So what is a qubit amplifier? So I told you now at least 10 times now, you cannot amplify a photon. And now I will tell you, actually you can. But the point is, you can from time to time. And it's also if you just want to clone a photon, or from time to time, you can clone it, no? But of course not all the time. So you can have a measurement where it has no outcome, but when you have an outcome, you know the result. It's like if you have this state discrimination, if you have two photons in two polarization, no, are not orthogonal. If they are orthogonal, I can distinguish them. But if they are at a certain angle of 30 degrees, I send you photon like two, you don't know which one it is. You can still make a measurement where you can be sure which one it is, but it won't work all the time, no? And the idea, you actually use some by some losses, polarization-dependent losses that you're, well, in case you don't know it, I think it's quite nice, no? Let's say I send you this polarization. One photon is polarized in this direction and one is in this direction. And this angle is not 190 degrees, so I cannot be sure. But I can do it. I introduce some polarization-dependent loss in this direction, let's say. So I send it to some medium with polarization-dependent loss. And then I end up with these states here, no? And now they're orthogonal. And I can measure it, no? It's nice. But of course, the price I have to pay, I have loss. So this doesn't work all the time, no? Many times, photon is absorbed. And it's the same thing with this qubit amplifier. It doesn't work all the time. And the idea is, we have a source again. No? We send one photon to Bob, one to Alice. So here I make this measurement, as I told before, with a setting and so on. And now to Bob, in order to increase these probabilities, I use this amplifier. And actually what I do, I use a teleportation scheme. You see, well, this is, maybe if you remind a bit the scheme I'd shown you before. Now we have here, this is our entanglement source, kind of source here, no? I said one photon here, and here we have one photon coming and we make a Bell state measurement. No? That's roughly the idea. And I can do this actually also by amplifying. In the teleportation, I don't amplify, no? But I can actually amplify it if I put here a transmission here, which is not 50%. Not 50%, but much more light goes here. So what I'm using here actually is this, again, this single photon entanglement somehow, no? But what I do, here I have a polarization qubit, no? So this means I have a horizontal or vertical photon. And here I prepare two single photons, one vertical and one horizontal. Now the photons can go here or can go here, no? With this probability here. And now, what's nice, if I detect here in the middle, so it's a bit simplified here, no? But I have detector which can distinguish between H and V. So let's say I get two clicks here in the middle, no? Which are a H photon and a V photon, for instance. So let's suppose here this photon was a H photon. So if I detect a H photon and V photon, then of course it must be the V photon which was reflected now. And now if I detect a photon here, it must be an H. That's what I want, no? Because I sent in an H. But that's the idea it works, no? So I can make this transmissivity very big. So most of the time the photons goes here, but when one of the photons goes here and I make a measurement here, the chance is quite high that they get it here. So if after a long fiber, the chance to get a photon eventually here is quite small, much less than this 82.8%, I can make this amplifier here, and with a small chance, I get an heralding thing. But once I get this heralding signal, the chance I detect it here is high again. And that's the important thing. I don't need a chance of 82.8% for the whole thing. But if I get a herald, and the machine tells me, OK, now it works, then I have this conditional probability of 82.8%, that's good enough to make this violation of a Bell inequality. So with a scheme like this, in principle, I can go very, very far and can still have this device-independent scheme. Well, provided I have very good detectors and so on. Then maybe you can say, OK, don't trust the detectors, whatever. OK, well, this is just now a bit, unfortunately, the truth is that if you model this and so on, you realize that the distances you can get with trusted and untrusted detectors, now it's not so long, no? If you have sources on demand, no? Then you can go to 100 kilometers roughly. But we don't have this, no? We don't have single photon sources on demand. We only have heralded single photon sources. And if you have heralded single photon sources, even if you trust the detectors, you can go, what is it, 15 kilometers. And again, like before, no, we're being very optimistic and so on. Okay, so I'm now coming to a conclusion. So my conclusion is actually QKD is ready for application. So there are a few companies who sell this, and with not that much success, but still. We are still limited in distance and rate. And this device-independent thing is a very nice idea, and there's quite a lot of research on that. Not only on QKD, but also on random number generators, because random number generators is also something very fundamental, and you can do the same kind of device-independent random number generator where you can remove all kind of defects your random number generator could have, and in NIST they build up a device like this, no, with superconducting detection and everything, and it's very nice, but the rate I don't remember now, it's maybe 1 bit a day or something, but if you have a very hard decision to take, no, it should be random, you can go to a NIST server and you get the best random bit you can imagine. Well, now, of course, this quantum repeaters, as I saw, is unfortunately still very unrealistic, and I would call this trusted repeater not democratic, no, because it's not for users like we are. It's, of course, for the powerful guys. Okay, thank you very much.